Hello, today we will be talking about synthesis and decomposition reactions. Now, these reactions you would have seen last year, but once again, what we're going to be doing this year is just going a little bit more in depth and looking at some specific examples with them. So, if we take a look down here, synthesis reactions, this is our general form. Okay, so typically we're gonna have two or more. It doesn't always have to be two. It could be three or four or five or however many smaller reactants, and they're gonna combine to make one larger product. So here is our general form. We have A plus B, so we have two things here combining. Once again, that stands for yields, and we're making a bigger product, a bigger compound. Okay, so that here is the general form of our synthesis reaction. So if we turn the page here, we have an example. So we'll try this one out. So it says determine the balanced chemical equation for the reaction of zinc and sulfur. So the first thing that we're going to do, once again, this is our word equation, is we're going to put it into our formula. So zinc is Zn and sulfur is S. Okay, now, once again, something that we need to make sure that we have is that we have our states. So zinc is a solid at room temperature, and so is sulfur. And once again, these are going to be combining to make a new compound. Okay, now in order to figure out what that compound is, what we're going to need to do is first we're going to have to figure out, is this a molecular compound or an ionic compound? So I have a metal and a non-metal, so this would be an ionic compound. So in order to do that, we need our ionic charges. So if you go to your periodic table, I'm going to pull it out right here. Okay, here's my periodic table. So I have zinc. And if you take a look at your periodic table, you can see that there's a 2 there, and that 2 means that it makes a 2 positive charge. If you're not sure about that, you can take a look at the key, which is on this bottom right-hand side, and you take a look at oxidation states, and that is what tells you what your charges are. So zinc is a 2. So I'm going to go back here, and what I'm going to do is I'm going to put it up top. Zinc makes a 2 positive charge, just like that. Okay, that's a Zn2 plus. And sulfur, once again, if I go back here, okay, if you take a look at your charges, the one that is bolded, because you'll notice that there's more than one here, the one that is bolded is -2. And because that means it's its most stable ionic charge. Another way you can remember that is that if you look at your groups, all of these alkali metals make a 1 plus charge, or they have 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, 8 for the noble gases there. So because these only have 6 electrons in its valence shell, they're going to pick up 2 electrons, and it makes it 2 negative. So we have sulfur, which is 2 negative. So because I have a positive and I have a negative, I'm going to do my crisscross. And when I do that, the final compound will be ZnS. Okay, now once again, the 2's cancel each other out, so we're given that there. Now at this point in time, we don't have, we're not too sure how to name this compound, or put the state of that compound. So once again, that's something that I would have to tell you. However, zinc sulfide is this right here, which is also a solid, and we'll be figuring out how to figure these out later on in this unit. Okay, and that's what we have here. So once again, very simple, right to the point. We have 2 smaller compounds coming together to make one bigger compound, and that is our synthesis reaction. Okay, now one thing I do want to point out is sometimes you may see this. Sometimes you may see this. Okay, let's say we have this same example here. We have zinc, which is our solid. Sometimes you may see sulfur that has an 8 there. Okay, and once again, it's still a solid. Now, the reason why you may see this 8 there is because typically in natural world, when we see sulfur out there, it's actually almost like in an octagon shape. Okay, there's 8 of them all the way around, and that's actually where they're the most stable. They make some octagon shape there. Okay, so if you do see this, nothing changes, right? So if I had zinc, if I had sulfur with the 8, once again, I'm doing the same thing. Zinc is a 2 plus, sulfur is a 2 negative. It doesn't change the charge. Okay, the only thing that it's going to change is the balancing. So once again, these 2's are going to cancel each other out. So I have zinc sulfide. It's still a solid. It's not changing anything. The only thing that you're going to need to do is that this 8 is what we're going to be balancing. So I need 8 sulfurs here, and then I'll also need 8 zinc there. So that's the only thing it's really changing. On a test, I'll accept either or. If I ever ask you a question with sulfur, if you just put S like that, or if you put an S with the 8, I'll accept both. The only thing that you need to make sure that you know how to do is balance it correctly. Okay. So that's essentially what a synthesis reaction is. However, like I said, we're going to be looking at more special cases in grade 11. So the first special case here, maybe we want to put a star beside it, is our synthesis, and this stands for reaction involving hydrogen. Okay. Now, any reaction that involves hydrogen is going to produce a lot of energy. Okay. Once again, like our sun, and the heat that we get is from a lot of reactions with hydrogen. The sun is primarily hydrogen and a little bit of helium. Now, however, what is most important is this point right here. When we're predicting our products, we use the crisscross method, but what we're going to be doing is we are going to assume, or we're going to treat hydrogen like a metal. We're not going to treat it like a non-metal, so it's going to be more of an ionic compound. Now, the reason why this happens is because if we take a look at this periodic table here again, hydrogen is in this group right here with our alkali metals. And the reason why it's there is because hydrogen forms a 1 plus charge. It acts like one of the metals there, okay, even though it's not a metal. Okay, hydrogen is a non-metal, but it's still placed on that side. So what we're going to do, let's do an example. That's the easiest way for us to kind of get an idea of this. So we're going to try this one here. It says predict the product for the reaction of bromine and hydrogen. Okay, so what we're going to do is we are going to write out what we have here. Okay, so we have bromine and we have hydrogen. So I'm just going to go in the order that I see. Okay, so I have bromine, which is Br. Now, once again, you need to remember your diatomic molecules. And if you're not sure what that are, all you have to do is just a quick Google search if you're not too sure, or it's also in our textbook if you search up diatomic molecules, and it'll tell you what they are. There are 7 of them. Okay, now if you take a look at your periodic table, those 7 are 1, 2, 3, 4, 5, 6. So iodine, bromine, chlorine, fluorine, oxygen, nitrogen, those are 6. And then hydrogen is the 7th. Each of those 7 have a 2. That's how they're the most stable. So bromine here has a 2 there. Plus hydrogen, also one of our diatomic molecules. Now, bromine is a liquid at room temperature. Hydrogen is a gas. Okay. So once again, what's going to happen is, well, typically if we took a look at this, we would say, well, both of these are non-metals. So this would form a covalent compound or a molecular compound. But with our special case, hydrogen actually acts like the metal. So what we're going to do is we're going to treat hydrogen like the metal, and we're going to treat this like an ionic compound. And when I say ionic compound, this is where our charges come into play. So because hydrogen makes a positive charge, it comes first. So we have hydrogen 1 plus, and we will have bromine, which is a negative. It is a 1 negative charge. So once again, 1 positive, 1 negative. When we do our crisscross, we would get HBr. Okay, now once again, when you're doing this, you don't have to put that top part there. I'm just doing it to show you. Once again, on a test, I would just be looking for that there, right? Obviously, we have our states and so forth. Now, at this point, we still don't know how to come up with the state of this. We will when we look at double displacement reactions. So for now, I would just tell you what it is. Hydrogen bromide is a gas, okay? And the last step that we need to do is we just need to balance this here. So what we're going to do, we have 2 bromines, we have 2 hydrogens. Obviously, we would need a 2 there, so we're going to put that 2 in the front. And that is our reaction here involving hydrogen. Okay, so let's keep on moving along here. Okay, our next question, or our next special case, is our synthesis with metals with oxygen. Okay, so we'll be seeing this one quite a bit actually, so you want to make sure that you are starting it, paying attention. And what I'm going to ask you to do, if you have these notes printed off or not, or if you're writing them out, there's 2 parts to this question. So the first part is this here, and I'm going to put part 1. Okay, this is the first part, which is that first bullet point. Metal and an oxygen will make a metal oxide. Part 2 is if you were to take that metal oxide and you mix it with water, you will produce a hydroxide base. Now, you may ask yourself, what is hydroxide? Well, if you go to your polyatomic ion sheet that I've also given to you guys, you can find this on the course website. Hydroxide is right here. It says OH, and it is a 1 negative charge. So I'm just going to put that here just to remind myself in case I forget. OH 1 negative. That is what hydroxide is. Okay, so once again, I always find that the best way of learning something, especially something new, is by doing examples. Okay, so once again, let's go ahead. Let's flip this over to the next page, and we're going to work our way through one of our examples here. So it says write a balanced equation for the reaction of magnesium with oxygen. Okay, so what we're going to do is we're going to start off by writing magnesium and oxygen, and it should be a synthesis reaction because that's what we're dealing with. So we have magnesium, which is Mg. This is a solid at room temperature. It is a metal. And we have oxygen, and it's nice that oxygen is given like that if you don't remember your diatomic molecules, and you should also know that oxygen is a gas. So we are mixing these two here. When these two get mixed, we will be making an ionic compound. Once again, metal and non-metal. So magnesium is a 2+ charge, oxygen is a 2 negative charge. When I do these crisscross, the 2's cancel each other out, and I'm left with magnesium oxide, just like that. Okay. Now, magnesium oxide is in solid form. So once again, like I said, we don't know that yet. We will learn it a little bit later. And lastly, what we're going to have to do is just finish balancing this equation. So I have 2 oxygens here. So I'm going to need 2. So I put the 2 in the front. But at the same time, it gives me 2 magnesium. So I need a 2 there as well. And that's my balance equation. So that is part 1. And I'm just going to go back here to where it says part 1. And it says this. A metal and an oxygen will make a metal oxide. So I have a metal, which is magnesium, and I have oxygen, and it's making a metal oxide, magnesium oxide. So the only thing that's changing in this formula is which metal you're given. So you could have magnesium, you could have copper, you could have sodium. It doesn't matter. Whatever the metal is, that's the only thing that's changing in this formula. Okay, so for part 2, what we're going to be doing is we are going to be making a hydroxide base. Okay, so what we're going to do is we're going to take our metal oxide, and once again, I'm just going to go back here because it says if you take your metal oxide and mix it with water, we can make our base. So I'm going to take that base, or sorry, not that base, that metal oxide, which is magnesium oxide, and I'm going to mix it with water. So I have magnesium oxide, and once again, it's still solid, and I'm mixing it with water, and we should all know that water is a liquid. Okay. Now, one common mistake that a lot of grade 11s will make is that they will bring this balancing down here, or this number. Okay, it could be a 2, it could be a 3, whatever the case may be. But a lot of people will bring that down, and that's incorrect. And the reason why that's incorrect is because this 2 here is only for balancing purposes only. So because you have 2 here does not mean you have 2 there. After I balance my final equation, I may have a 2 there, but it doesn't always work out that way. So the last part, I'm making my hydroxide base. So my hydroxide base, and once again, it's going to look something like this. It's going to look, I'm going to have my hydroxide base. Hydroxide is OH, 1 negative. But I'm going to need something in the front. Because once again, it's a synthesis reaction. 2 things coming together to make something bigger. Now, if you take a look at this equation, if you remember your law of conservation of mass, things cannot be created or destroyed. So if you take a look at this equation, you have oxygens. Okay, so oxygen is accounted for, oxygen is accounted for, hydrogen is accounted for, hydrogen's accounted for, but what isn't accounted for in this reaction? And that's your magnesium. So what will be joining this hydroxide? It's going to be your metal. So if I have magnesium here, magnesium is a 2 plus charge. So when I do my crisscross, I get Mg bracket OH2. Okay. And this here, once again, we don't know this yet. We will later on. This here should be aqueous. Okay. So just to kind of go back to that second part, when you have your metal oxide and it's mixed with water, it's going to make a hydroxide base. And that's what we just had here. We had our metal oxide, which is what we created up there. We mixed it with water. Okay. Essentially what we're doing is we're dissolving it in water. And when we dissolve it in water, we're going to get this hydroxide and whatever metal we also have, which is magnesium there. Okay, so let's try one more example, okay, before we move on to the next one. Okay, this is not part of the notes, so I'm just going to do it on a separate sheet here. Okay, now I would like you to do the exact same steps as we've done before. However, instead of magnesium, I would like you to use sodium. Okay, sodium, which is Na. So I would like you to pause this video, and what I want you to do is I want you to start the exact same question over again. So part 1, the only difference is it says write a balanced equation for the reaction of magnesium with oxygen. I want you to change magnesium into sodium. Okay, and I want you to do those 2 same steps again. Okay, so pause the video, try it out. When you are done, click resume, and we'll see if you got that correct, okay? So take a second now and try that out. Okay, so hopefully you did pause it, okay, to attempt this. So once again, we're going to do our 2 parts here. We have part 1, okay? And part 1 states that we're going to take our metal, which is sodium, okay? It is a solid at room temperature, and we're going to mix it with oxygen, and oxygen's our diatomic molecule. It is a gas here, and what we're going to be making is a metal oxide. So sodium is a 1 plus, oxygen is a 2 negative. When we crisscross these 2, we get Na2O. Okay, and this here is solid. Okay, so once again, we have to balance our equation. So I need a 2 over there, and oh, actually, we need a 2 here. Sorry. Okay, I made a mistake. See what happens when you make a mistake? You could always catch it. So I need 2 oxygens. So I have 2 oxygens, but this gives me 4 sodium. So I just need a 4 there instead of a 2. Mistakes happen to the best of us, but that's okay. If you go slowly and you check your work, you should be fine. Okay, so part 2. We're going to take our metal oxide, which once again, we don't take the 2, we just take the compound. So it's Na2O, which is a solid, and we're mixing it or dissolving it in water. Now, when we do this, we're going to be making our hydroxide base. So we know it's going to end in OH, and we know it's going to end in OH because the negative charge always comes second. The positive charge always comes first. So our positive charge in this case is our sodium, which is a 1+. So when we do this here, we are going to make sodium hydroxide, and it's aqueous. Once again, we don't know that yet, but we will later on. And then the last thing we need to do is we need to balance this out. Okay, so if I take a look here, I have 2 oxygens, 2 hydrogens, 2 sodiums. So I have 2 of everything on this side, but I only have 1 of everything on this side. So this one's nice and easy to balance because I just put that 2 in the front and everything is balanced. Okay, so this is our synthesis with metals with oxygen. So once again, this is a little bit different than what you guys looked at last year. And like I said, we're just taking it a little bit further in grade 11. Okay, so if we go back to our lesson. Okay. Hopefully you guys can see that there. Okay, the next one is our non-metals. Okay, so we're going to have 2 parts again. Okay, now just a little bit different. So you're going to have the same 2 parts. Okay, so the first part, and I'll just write this out. Okay, our first part is, sorry, I'm going to try to get the exact same here. Okay, so part 1, we're going to take, this time, we're taking a non-metal and we're mixing it with oxygen. And this is going to make a non-metal oxide. Okay, so that's part 1. And it's very similar to our last one, but instead of using a metal like magnesium or sodium, we're going to use a non-metal like carbon or sulfur. So it's the same steps. Okay, now, one thing that you need to make sure, or not sure anyways, one thing, you will be typically told which oxide you're forming. Okay, so if you had carbon and oxygen coming together, I would tell you which one you're making here. I would tell you if it's carbon dioxide, carbon monoxide, carbon trioxide, whatever the case is, you would need to know that information there. Okay, for part 2, we're going to take that non-metal oxide and we're going to mix it with water. Now, when we do this, instead of making a base like we did last time, right? This one here, hydroxide, is a base. We're going to be making an acid. Okay, now which acid are we going to make? We're going to make the ic acid. That is the normal acid. Okay, so once again, all of these points are very important, but once again, we could kind of summarize it into 2 parts just like we did before. Okay, so what we're going to do is we're going to try some examples here and get a little bit more familiar. Okay, my pencil just died, so I'm going to try and find a marker that I can use, or a pen anyways. Okay, so let's go ahead and let's try an example here. Okay, so the first one we have is our part 1. So we're going to write a balanced equation for the reaction of oxygen with carbon to produce carbon dioxide. So once again, as you can see, I'm telling you which one you're making here. So we have carbon. Okay, carbon is actually a solid nonmetal, and we're mixing it with oxygen, which is our diatomic molecule. And we are making carbon dioxide. Di means we have 2, so we're making CO2, and carbon dioxide is what we breathe out, so you should know that that is a gas. Now, this one's nice because you don't have to balance anything, so we can move on to part 2. Part 2 is that we're taking this carbon dioxide gas and we're mixing it with water. So this time we are making an acid, and we're making the ic acid, which is the normal one. So from previous, you guys should know that our ic acid is carbonic acid, and that's our HCO3. Or sorry, I forgot the 2 there. H2CO3, and this is aqueous. Okay. Now, once again, how did I get this here? Well, it has to do with the ic acid. So there's carbonic acid, carbonous acid. You could have percarbonic acid, hypocarbonous acid, right? Those are all those acids that we looked at before, but the one that we're looking to make is the normal one. So in your polyatomic ion sheet, if you take a look, once again, you have the normal atom, and if you look over here, your acids, it's the ic acid, the normal one. Okay, and that's the one that we should be always making. Okay. So what we're going to do, we could try one more example here to get a little bit more comfortable with that. Okay, so we're going to write part 1. Okay, so if we would get an example like this, we will have, let's try, I'm going to write it out here. So we're going to have, write a balanced, oh, I'll move this over, sorry, write a balanced equation of oxygen, and this time we'll change up to phosphorus. To make phosphorus trioxide. Okay, so part 1, you're going to come up with this equation of oxygen and phosphorus to make phosphorus trioxide. And then I also want you to try part 2. And this is where we make our ic acid. Okay, so once again, just like before, pause the video and try both of them out. And then when you're done, resume it and you can see if you did this correctly. Okay, so take a second and try that out. Okay, so hopefully you did try that out. So what we have here, okay, I'm going to start off with phosphorus. I know it has oxygen first, but I know that it's going to be phosphorus first, then oxygen. So I'm just going to kind of keep it similar. So I have phosphorus. Okay, phosphorus is phosphorus, I believe, should be a, sorry. Let's figure out here. Phosphorus should be phosphorus at room temperature, right? This is solid, sorry. Took so long to figure that one out there. Okay, so it's solid at room temperature. I just don't have my class or school periodic table in front of me. But anyway, so we have phosphorus, which is a solid, plus we have oxygen, sorry, which is O2, which is a gas here. And when these two come together, okay, we're going to make PO3. And this here should be also a gas at room temperature. So when these two do mix, once again, we're going to have to balance this out. So I have 3 here. I got 2 there. So the common denominator is 6. So I'm going to put a 3 over here. That gives me 6 oxygens. I'm going to put a 2 over here, which also gives me 6 oxygens. So those oxygens are balanced. And lastly, my phosphorus, I'm just going to put a 2 there. So the next step is I'm going to take this PO3, which is a gas here, and I'm going to mix it with my water. Now, we should make the ic acid. So our ic acid, once again, if we take a look at our polyatomic ion sheet, okay, if we have phosphate, which is the normal atom, we should be making phosphoric acid. And phosphoric acid is H3PO4. Okay, and this is aqueous. Okay, now once again, if you're a little bit confused on how we do that, okay, PO4 is phosphate and there's 3 negative charge, and that 3 negative charge means that we need to add 3 hydrogens to balance it out. And that's how we get that there. Okay, so hopefully that makes sense to you. All right, so let's keep moving on here. Okay, the next thing we're going to be looking at is decomposition reactions. Now, the nice thing about decomposition reactions is that there are no special cases of decomposition reactions. If you're able to do your synthesis reactions, you should be able to go backwards and do decomposition. Okay, so anyways, what is a decomposition? It's a reaction where one larger reactant breaks up into 2 or more smaller products. Okay, and once again, here is our general formula, just like that. Now, so typically in the ones that we're looking at in grade 11, the compounds are going to decompose into their elements. So let's take a look at calcium oxide here. So write the balanced chemical equation for the decomposition of our calcium oxide. Okay, so we have Ca, calcium is a 2+, oxygen is a 2-. I know this because once again, this is an ionic compound. I have a metal and a non-metal, and it'll become CaO after we cancel things out. Okay, this is a solid at room temperature. Don't stress about that right now. We'll figure it out later of how to figure out that. Now, this calcium oxide is going to be decomposing into its parts, into its elements. So it's going to be decomposing into calcium. Okay, and calcium is a solid at room temperature. And it's going to be decomposing into oxygen, oxygen gas, and oxygen is a diatomic molecule. And the last thing we need to do is just balance. So I have a 2 there, so I need 2 oxygens there, and I also need 2 calciums. Now, like I was saying before, if you can do synthesis, you should be able to do decomposition. And the reason why I'm pointing this one out is because maybe you noticed this or not, but this here is one of our metal oxides. And if you take a look back at our notes, I'm going to try to find it here, okay? If you have a metal and you have oxygen, you make a metal oxide. So what we're doing is we're just going the opposite direction. We took our metal oxide and we made a metal and oxygen. So like I said, if you can go one way, you should be able to go the same, just the opposite direction. Okay, and now our last question that we have here is write the balanced equation for the decomposition of calcium carbonate, okay, to calcium oxide and carbon dioxide. Now, one thing I do want to point out, when a polyatomic ion is present, most times you'll be given the products or you test for them in a lab. So let's go ahead and let's try this one out anyways. So we have calcium carbonate and it's decomposing to calcium oxide and carbon dioxide. So the first thing we need to do is come up with calcium carbonate. Calcium is a 2+. Carbonate is CO3, 2-. So as you see, there's both 2's. They're going to cancel out into CaCO3. Okay, so for this question here, I'm not going to worry about the states. Okay, and it's going to decompose into calcium oxide. So once again, calcium is a 2+, oxygen is a 2-. So we get CaO. And we're going to get carbon dioxide, which is CO2. Okay, and once again, if we're taking a look at this, okay, don't worry about the states. Carbon dioxide, we should know as a gas anyways. But if you take a look, this is actually already balanced. So we're good over there. Calcium carbonate to calcium oxide and carbon dioxide. Okay, so hopefully this made sense to you. This wraps up this lesson here. And thank you guys for all listening.